Hello everyone and welcome to the channel. I'm Emmanuel, I'm an airline pilot, and in today's video let's talk about our engine instruments. Back in the days before I became an airline pilot, when I've been a flight simmer like the vast majority of you guys watching this channel, I of course had a generalized idea of what those engine instruments meant, but I never really knew how to interpret them for sure. In some cases didn't even know what exactly they were good for. In today's video, I want to teach you all of that and a little bit about the differences between engines and indicating systems as well. We are doing this on the example of the CFM56 engine in the Boeing 737, but rest assured that pretty much all aircraft are going to use the same indications with a couple of differences. For example, some manufacturers decide to use EPR instead of N1, or in the latest generation of aircraft, even a thrust percentage. Now, I will explain you exactly why that is the case and how to interpret each one of them. Now, let's go ahead and get started, and rest assured this is exactly the same between Boeing and Airbus, so it's done on the example of the 737 here, but you can apply this knowledge to your Airbus as well. We're going to start from the top to the bottom over here. The top instrument is usually the one that's actually telling us like how much thrust we produce. The majority of engine manufacturers choose to do this by the value of N1, while some others are going, for example, for EPR. We'll be talking about the differences in a few moments, but we are going to start with N1 over here. So N1 is a fictional value. Technically speaking, it represents the RPM of the fan at the beginning of the engine. So that's the big thing that you see rotating at the front of the engine. Now, you could obviously give us pilots the exact RPMs, but how am I supposed to remember whether I need 3620 RPMs versus 4190 RPMs? You can see this is a little hard to remember. For this reason, manufacturers simplified things and just made up a fictional percentage over here, where idle is usually around 20% and the maximum is usually somewhere just above 100. For example, for the 737 here, we can see that the red line is located at 104%. There are other engines running up to about 110%, so don't take the term percent per se over here. It is really just a fictional figure that you see. N1 has the advantage of being very simple, while it has the disadvantage of, number one, not giving us a linear relationship to the actual thrust output of the engine, and number two, not always giving us the same thrust output for the same N1 figure. Think of it like this. You got a fan rotating at 3000 RPMs. That equals, for example, 60% N1. But what happens if that fan has been hit by a couple of small rocks, and if it may have had a bird strike in the past and therefore has small damage marks? That fan, which may still be absolutely legal to fly, obviously there are certain tolerances defined by the lawmakers, that fan may not produce the same thrust output at the same N1 percentage as a brand new one. For this reason, N1 has the advantage of being simple, but has the two disadvantages of, number one, not giving us a linear idea of the actual thrust output, and number two, not even always giving us the exact same thrust output at the exact same N1 indication. Now, airplane manufacturers thought, well, how can we solve this? And they came up with a good idea, and that is the so-called engine pressure ratio, which we can see on the example of the Airbus A320's V2500 engine over here. Engine pressure ratio takes two pressures, the pressure at the engine outlet versus the pressure at the engine inlet. If there is a higher pressure at the outlet of the engine, then it is producing forward thrust. On the other hand side, if there is a higher pressure at the inlet of the engine, then the engine is actually producing drag. Therefore, an EPR of 1.0 is going to be neutral thrust, while an EPR, for example, of 1.2 means that you are producing positive thrust. Now, EPR, therefore, is a very good indicator to tell you how much actual thrust your engine is producing. The only problem is that the figure is once again rather complex and relies on complex measurement techniques. So first of all, we got 3 digits after the decimal, which can be rather difficult to memorize. So let's say we want a certain pitch and power setting for the approach. Pitch is easy, 4 degrees nose up. But how much power do you need? Do you need 1.125 EPR? That's rather difficult to remember and also rather difficult to command precisely with your thrust levers. Therefore, N1 much easier, EPR more accurate, but a little bit more difficult to control. And for this reason we are also referring to N1 percentages if we are talking about pitch and power figures with an EPR controlled engine, but that would be a completely different story now. So now we know what EPR and N1 is, and we know that both of them have their advantages and their disadvantages. So in a day and age where computers are the norm in aircraft, manufacturers thought that, well, we can combine those two. And that's how they created the thrust indication that you have, for example, on the A380, A350 and the Boeing 787, if those are featuring the Rolls-Royce Trent XWB engines. And what they're doing is that you take the example of N1 with an easy figure between 0 and 100%, and you mathematically compute the EPR figure into that thrust percentage, which you then show to the pilot. That makes it very easy to control your engines and gives you a very precise output. Remember, N1 is not linear when compared to the thrust percentage. The difference in thrust output between 20 and 40%, for example, is much, much less than the difference between 60 to 80% or even 80 to 100%. Engines are optimized to rotate at a certain speed, which is normally the cruise setting, so for most jet engines between about 70 to 90%, usually somewhere around the 80% figure, 80, 85-ish. While the engines are most efficient there, they also have the largest change in thrust percentage compared to the speed of the fan. Therefore, you can say that changing thrust between 60 to 100% has a much, much greater effect than changing it between 20 to 60%. So, a thrust gauge eliminates that problem and tells you a direct relationship. While it is technically more complex, the EPR gauge is the slightly lesser, because technically easier, gauge, which gives you, again, an accurate output, independent also of the aircraft or the engine's maintenance condition. But for simplicity, the N1 gauge is still used in most engines. So that much about the value that is used to command your engine thrust. We got a couple more, so sit back, get yourself a drink, and let's talk about EGT. EGT stands for exhaust gas temperature, and it means the temperature at a very specific point in the engine. Now, manufacturers can kind of define where exactly that is located. So in one engine it may be located a little bit further inwards than in another. What is important is that we are taking the temperature in one certain engine stage, and then we are computing the maximum temperatures that you may have in that stage of the engine. Now, this directly relates to all other stages in the engine, because even if the temperature in the combustion chamber may be 1000 something degrees and the EGT shows you 600, if the EGT goes to 700, the temperature in the combustion chamber rises in a certain relation. So EGT, made simple, is a temperature reading taken somewhere in the engine, and then limits are defined depending on that stage in the engine, but they apply to pretty much the entire engine. Now, why are those EGT limits important? Well, if the temperature in the engine becomes too hot, the metal of the engine gets weaker, and therefore engine damage may occur very quickly. For example, if you heat an engine a couple hundred degrees hotter than it can take, it's going to only take a couple seconds for the entire engine to come apart. Different EGT limits for different phases of the flight may be defined, and in modern aircraft are usually indicated by that red line over here. For example, during engine start you might often see it somewhere down here, and then in flight may go a little bit higher up here. So the electronic engine controls are continuously computing where the current limit for the engine is supposed to be, and then show you that on the gauge. The important reason we have that gauge though is because we need to prevent temperature exceedances in the engine, which are measured on the example of a temperature taken at some point in the engine, which then becomes EGT. Now from there we're moving a little bit further down and we got the fuel flow. Now fuel flow, you never really know how important that really is, because, well, in some cases airplane manufacturers are not even showing it over here. So for example in the 737 it's optional, the 777 doesn't have it up here at all. But what is fuel flow good for? It generally tells us how much the output of the engine is supposed to be. So if you have a certain fuel flow, in a certain situation you would expect a certain thrust. You don't need to know exactly how that correlates, that is what the electronic engine control systems of your aircraft are supposed to do, but you should know some general figures. Example, when you're in a typical cruise in the Boeing 737 with a CFM56, you're looking at thrust output somewhere around 80% and a fuel flow of about 1.2 tons per hour. If that fuel flow suddenly shows you 2 tons per hour in the very same situation, you know that something is wrong. You can suspect a fuel leak, or you can suspect mechanical damage to the engine, but you know that something's wrong. That's what the fuel flow is good for. Now, moving down then, those are the primary engine indications that we got up here. Now, if we just look at the Airbus example once again, they are showing us pretty much the same thing. We got the N1, we got the EGT, we got EPR where applicable, and we got the fuel flow. Airbus also shows us N2, and that is going to be the next thing that we are going to talk about. Boeing shows us N2 as secondary engine indication, and what exactly is N2? So modern jet aircraft or modern jet engines have more than one spool. You usually have what's called the low pressure section, which is where the pressure of the air ingested is still comparably low, which is your N1 indication. And then you got the high pressure section, which is where air has already been compressed quite a bit, is then ingested into the combustion chamber, ignited, and then pushed into the turbines. Now, that part where the air pressure is the highest, that's our N2. N2 is usually going to rotate faster than N1 because of the higher pressures down there, and the N2 is basically an indication that we can use to monitor when things are going wrong inside our engine. During the engine start, however, it's exactly the opposite. During the engine start, N2 rotates first, and so we control when to ingest or when to insert fuel into the engine during the startup procedure. Some engines are also going to show you an N3, especially Rolls-Royce is doing that a lot, which basically is a third spool with even higher pressure inside the engine. Now, I'm not going to go into details as to why you might have more than one spool in the engines here. Let's just say that the engine can be more efficient the more spools you have. Next up, and that is a variable gauge down here in the 737. In the Airbus, it is a gauge that you see all the time. Let's talk about fuel used. You can see Airbus gives us fuel used at the very top of the secondary engine parameters there. In the Boeing 737, in order to get fuel used, we got that little switch which we can use to turn the fuel flow indicator into a fuel used indicator. Why is that important? So the fuel used indicator tells us how much fuel the engines have already burned in this cycle. Now, this is important because it tells us exactly how much fuel we are supposed to have. It's a very easy equation. The fuel that you loaded on the ground before you started the engines minus the fuel that you used has to be the fuel that you currently have on board. If it is not, then you absolutely know that you have a problem. Now, there are always some tolerances within aircraft fuel systems, so in the A330, if like 500 kilos are missing, we don't get concerned at all. If it reaches 1000 kilos, then we know we have a problem. So, generally speaking, fuel total plus fuel used needs to equal the amount of fuel that you had before you started your engines. Otherwise, you have reason to suspect a fuel leak. Now let's go on to the type of gauges that I always had problems with when I used to be a flight simmer only. That's oil pressure, oil temperature, oil quantity, and the vibrations. What are those good for, and what do they tell us about our engines? So let's start with the oil pressure. Generally, oil in an engine is important because you got different parts that are rotating very quickly, and if they touched one another, the engine would immediately take damage. Therefore, we insert oil to make a boundary between those rotating layers of the engine. So, two things are important when we create that boundary between quickly moving parts in the engine. Number one, the pressure of the oil, which can easily be explained. Let's assume that you have a piece of air in a balloon. You can kind of compress that balloon a little bit. The further you compress that balloon, assuming that it doesn't rupture, the further you compress that balloon, the higher the pressure of the air inside it. The same applies to your engine. The higher the oil pressure, the more we know that we're getting into a regional problem. But the same applies the other way around. If the oil pressure is too low, then there is not enough pressure to keep the rotating metallic parts away from one another, and therefore they might touch one another, which then in turn is going to lead to damages. Therefore, the oil pressure tells us something about the condition of our engine. If the oil pressure is too high, we know that we got a problem. If the oil pressure is too low, we risk getting a problem because rotating metallic parts may touch one another. Now, what exactly does that mean for the practical use of the oil pressure gauge? So, if the oil pressure is too low, it means that bearings are losing lubrication, metal-to-metal contact can occur, rapid overheating and wear can occur as well, and all of that means a possible engine failure can happen. If the oil pressure is too high, it tells us that the strain on the system is too high, or that damages may have occurred to the seals, or that a leak of engine oil may be happening. Now, you don't need to know exactly what oil pressure you're supposed to have. Your electronic engine controls are going to monitor that. And your gauge is also going to give you red lines that tell you exactly how much you can have. The important thing here is oil pressure exists to ensure that the rotating parts in the engine aren't touching one another, and the oil pressure gives you an idea of the condition of the engine. From there we're going down to oil temperature, which kind of serves the same idea. So oil temperature is important because it tells us something about the health of the engine, the internal friction levels, and the effectiveness of the cooling level, as well as the overall engine stress. Imagine it like this. You got two metallic parts that are rotating. That creates a friction. Just like when you are moving your hands next to one another and move them quickly, you will eventually feel it getting hot. The same applies to the engine. But since the oil is in between the moving parts of the engine, the oil is getting hot instead. Therefore, the temperature of the oil gives us an idea about how well everything is running in the engine, and gives us an idea of whether the friction is getting too strong, or which in turn can indicate problems with the bearings, etc. So, what happens if the oil temperature is too high? Basically, the oil becomes thinner and therefore has less chance to keep the metallic parts from one another. This means the overall lubrication effectiveness decreases and the wear of the engine increases with the potential for engine failure. If the oil temperature is too low on the other hand side, the oil becomes thicker, therefore has a poorer circulation, meaning the oil just can't get in between all those rotating parts well enough. This in turn increases the drag inside the engine and leads to an inefficient lubrication. Now those are the two meanings for the oil pressure as well as the oil temperature. Generally speaking, again, normal values will be recognized by your electronic engine controls, and if they go abnormal, then it's a good idea to have in mind what that may indicate. But from a pilot's perspective, if they go out of the ordinary, you generally just have one course of action: shut the engine down before it destroys itself. The one thing that the oil system is important for is to avoid metal-to-metal contact inside the engine, which will lead to an almost immediate destruction of the engine. Therefore, the most important thing here is to avoid those rotating engine parts touching one another. That is what the oil is doing, and the pressure and the temperature gauges just give you an idea of how well that is running. Lastly, we got the oil quantity. Now, the oil quantity is always taken in the oil reservoir. When the engine is started, oil is sucked from that reservoir into the engine. Therefore, we only care about the oil temp or the oil quantity indication here on the ground. In the air, you use it to a certain extent, because you always have to have a certain minimum that the engine manufacturer is going to define, but the indication is always going to go up after landing when the engine is turned off. So generally, you just have a minimum figure that's going to be defined by your engine manufacturer. You make sure that you have that on board, and only if the quantity starts dropping too far in flight, that's when you start getting concerned about having an actual oil leak. Now let's move on to the engine's vibration. Vibration gives us an idea of something in the entire rotating mechanisms of the engine not being right. Generally speaking, a perfectly balanced engine is not going to vibrate at all. However, no engine is perfectly balanced. For example, one fan blade may have caught a little rock during a landing. There is a small bit of damage which the engineers can easily correct for, and then the engine is started again. Now we will have an imbalance between two parts of the engine that are moving. That means the engine is going to start vibrating. This vibration is tolerable and absolutely normal during engine operation. However, it may not exceed certain limits. If the vibration goes higher, it tells us that the imbalance in the engine is getting stronger. And this in turn creates forces because of the rotation of the engine components, which can eventually exceed certain limits. For example, in the Airbus A330, we generally start getting nervous from a vibration of 4.0 units. The indication itself is again just an artificial number that is made up by the engine manufacturer to make it easy for the operator, aka the pilot, to understand how strong the vibration currently is. Now, here again, all you need to know is that the stronger the engines vibrate, the worse of a maintenance condition they have, and if a certain limit is exceeded, that tells us that there is such a strong imbalance in the rotating parts of the engines that damage may occur. In the worst case, the rupture, for example, of a fan blade or an entire turbine. Now that's what vibration is used for. And this basically covers the types of engine instruments that we are seeing and that we're using to control our engines and to monitor our engines. Now there are a couple more things that I just quickly want to talk about, and that is common warning lights that we may see. So, a couple of things worth noting here. The 737NG gives us 3 warning lights. In the Airbus we don't have lights because we have ECAM messages popping up when something happens. Now, what do those mean and why are they important? Well, the upper one is the starter, which tells us when the starter is engaged. That one is basically only important for monitoring during the engine start, when the start valve open light illuminates. The one below that, however, is a really important one, and that is the oil filter bypass. Now, the engine is equipped with a filter in the oil system in order to ensure that if very small contacts occur, like every now and then, the small pieces of metal that are generated by this are removed from the oil system before the oil re-enters the engine. When that filter clogs up, it tells us that there is a lot of contaminants in the oil, which is an indication that internal engine damage is happening. Therefore, in order not to completely shred the engine when that happens, a filter bypass is built in by the engine manufacturer to prevent an immediate destruction of the engine when too many contaminants get into the oil. However, when that bypass activates, we know that there is a problem with the engine, and in many cases we are just going to shut it down to preserve engine life. The last one is the most important one. That is the low oil pressure light. As I outlined when I explained the oil indications and their meanings, oil is just as important to the engine as fuel or air. When you have a low oil pressure, it means that the rotating parts of the engine can't be kept away from one another well enough, and therefore contact may occur, which can lead to the immediate destruction of the engine. Therefore, the low oil pressure warning is one of the most important ones we got for the entire engine, and is a very strong indicator to shut the engine down. Well, my friends, and those are the engine indications in pretty much any aircraft. Thank you very much for watching. I do hope you found this one interesting. As always, this is not a complete explanation as you might expect it for an engineer, but this is a simplified explanation for flight simmers and, for example, for, a student pilot starting to fly. But I do hope that this gives you a very good insight into what those engine indications mean and why they are important. Thank you very much for watching. As always, if you liked the video, then like, comment and subscribe. Leave your feedback in the comments underneath, and with that I'm really looking forward to see you all again on the next one.